Hello, and welcome to Lecture 4 of Superposition and Interference in Phys 1201. And this is the first in a series of 2 lectures about two-source interference. And it turns out that two-source interference is one of the most important experimental ideas in physics, as we'll see at the very end of next lecture. To understand some of the things that we're about to talk about, we need to take another look at waves leaving a source and just remind ourselves that generally when waves leave a source, they go in all directions. So here's an example. This is an animation that I've made, and this black dot here is representing the source. And so this could be a speaker, or since this is one dimension we're showing, perhaps this is a rope, and this is a point on the rope that we are holding and shaking up and down. And so each time we shake it up, a crest is formed, and that crest then travels in both directions. And so we get something that looks like this. This is really no different from what we were looking at in an earlier lecture when we were talking about waves leaving a source and going in all directions in a plane, say, so that you get circular wave fronts that travel out. But here they travel out in all directions on a plane, whereas here we're in one dimension, and so the only two directions possible here are right and left. So this animation is going to have two sources in it. We've got one source here and one source here. And so each of these will send waves in both directions, although we're not going to see the ones going left from this source because it's over at the left edge of our picture. And this is going to be very similar to animations that we looked at earlier showing standing waves. And in fact, if you watch it, you will see that part of it is a standing wave. So I'm just going to pause this for a moment here. Over here, this is a standing wave. You can recognize that as it goes, it's got nodes here and here and here and here. So you can see those nodes where the blue curve, which is the total wave, isn't moving at all, and antinodes halfway in between. So what's going on in here is exactly what we talked about with standing waves, and that's not surprising because we've got waves going in both directions and they're identical. And we know that when we have waves traveling in opposite directions, meeting and interfering, we always get a standing wave. But on this side, things are very different. If you watch what happens as a red wave crest comes along, it reaches this source just as a green crest is being emitted. And so it ends up traveling this way on top of the green crest. And so they add together and we get constructive interference everywhere out of here. Now, that looks totally different from a standing wave. This is now a traveling wave, and it has twice the amplitude of the waves coming from each source because they're perfectly adding up constructively everywhere. Just imagine if these were water waves, if you were sitting here, the water under you wouldn't be moving at all because you're at a node. You can see the blue curve here isn't moving. If you were sitting here, the water would be going furiously up and down. You're at an antinode. But no matter where you are out here, I'll just pick a random place, the water under you is going up and down and up and down. If you look here as well, the water under you is going up and down. No matter where you look out here, you get constructive interference in a traveling wave, in contrast to the alternating constructive and destructive interference of the standing wave in here. And so it has to do with the fact that in here, the waves from the two sources are going in opposite directions, and we've seen how that adds together to make a standing wave. But here, they're going in the same direction, and things are arranged just right so that the crests of one always end up on top of the crests of the other. We can understand more about the animation that we just watched if we think about it using path length difference, which we saw in a previous lecture. So I've drawn the two sources with these pink X's. And here is the green wave going out of this source in both directions, and the red wave coming out of this source in this direction. And I've drawn the waves above and below because I wanted to show them to you, but then I want to get them out of the way. So I'm going to move them up and down so that they're out of the way, so that I can draw some other things here. But one thing to notice, if you look back at the simulation, is that the distance between the sources that I chose, so I'll call that distance d, that distance is 2 times the wavelength. On this drawing, you'll see the wavelength is 4 grid units on the graph paper, and the distance between the sources is 8. And so we have in this setup that d is 2 lambda. And I could have chosen any value for d. It doesn't have to be 2 lambda. That's the one I chose because it gives us a particular case. Now, let's pick a point where we know what's going to happen. If you look at these waves, you can see this trough on top of this trough, and you know that right here has to be an antinode. So we already know that that's an antinode, but let's understand why. So there is a path length from this source to here, and from this source to here. So let me call this path length R1, and I will call this path length R2. And note that R1 is 6 units, so that is 1.5 lambda, right? 3 lambda over 2. And R2 is 2 grid units, that's half lambda, lambda over 2. And so our delta R, I'll choose to make it positive, so I'll take R1 minus R2, and so it's lambda. Well, we saw before what that means. That means that crests arriving here from this source are arriving at the same time as crests sent from here, a full cycle, a full period earlier. And so we know crests and crests have to arrive at the same time. On the other hand, if we look, say, here, now we have an R1 like so, and an R2 like so. And our new R1 at this point is 3/4 of a lambda, 3 lambda over 4. And our R2 is 5/4 of a lambda. And so our delta R is lambda over 2, half a wavelength. And that means that crests arriving here from this source are arriving at the same time as whatever was leaving here half a cycle earlier, and that would be troughs, and so we get destructive interference here. Now let's look at any point out here. And I'm just going to pick a totally arbitrary point. And I'm going to say that this distance here is, I don't know, I'll call it big R, just to choose a symbol. Now, notice what that means. That means now we have our two path lengths. We have R2, and we have R1. And note that this is D. R1 is just D plus big R. And so we just have that R2 is big R, R1 is D plus big R, and so delta R is just D. but we already know that that's 2 lambda. And so that means it's going to be constructive interference. We have an integer number of wavelengths, so troughs arrive at the same time as troughs. And so this will be constructive interference. But note, I picked an arbitrary point. I could have picked anywhere out here and called it R, and I would have come to the same conclusion. And so that tells us we have constructive interference everywhere out here. Let's look at another example that shows that things can turn out very differently. So here are 2 sources again, but I'm going to point out to you that the distance between them is now, look, 1 wavelength and another half wavelength. So the distance between these 2 sources is 1.5 or 3/2 of the wavelength. Now remember that it is the blue curve that is the total wave that you would see anywhere, and I'll start up the animation, and you see once again we get the standing wave in between. We have to, right? We've still got identical waves propagating in opposite directions. But now out here things are totally different. We've got a flat line. So notice that now whenever one of the red peaks arrives at the other source, it arrives at just the same time that a trough is being formed there. And so they interfere destructively, perfectly destructively, and we end up with no wave at all out here. So no matter what, we always get a standing wave in between the 2 sources. But what goes on outside of the 2 sources depends on the distance between them. We've seen the case of completely constructive interference and the case of completely destructive interference. And for other distances separating the 2 sources, you can have intermediate cases that are neither perfectly destructive nor perfectly constructive. Now let's quickly go through the same argument with path length difference that we saw before. So I've drawn it the same way, but now if you look, you will see that the distance between the sources is 1.5 lambda. There's lambda, it's 4 grid units again. And there's D, and it's now 6 grid units. And so D is now 1.5 lambda, 3 lambda by 2. And we could go through the argument again for some points in here between the sources, and we would find again that there would be places where we would see full integer wavelength path length difference, and so those would be areas of constructive interference. And we would see other places with half integer path length differences, and so those would be destructive. But now let's look out here. So again, I'm going to pick just an arbitrary point, and I'm going to call the distance out to it capital R again. And so again, we would have an R1 like so, and an R2 like so. And again, R1 is D plus big R, and R2 is just big R, and so our delta R is again D, which is 3 lambda over 2. And since that's an integer, or a half integer wavelength, that tells us that crests from one always arrive at the same time as troughs from the other, and we will have destructive interference out here. And that's true everywhere out here, because I could have picked any R and this argument would be the same.